Okay, so let's get started here. So when light hits a thin film, some of the light gets reflected away from the material. All right, so in this picture, we can see that light is traveling from air, and then it will hit whatever the film material is. So say soap, or oil, or what have you, and then some of it will just reflect away. Right, so ray one, we can see just hits the material and then gets reflected away. Okay. But as we saw from, we discussed this a little bit in the last chapter, the chapter 9 material, when light rays pass from a medium that is less dense to more dense, the ray gets refracted, right? So it gets bent away from its initial direction of travel. Okay, and so the ray that gets refracted inside the film material has to travel a certain distance t into the material, and then what happens is it hits a kind of a bottom layer. Okay, and again the same kind of thing happens. It hits the bottom layer, the ray gets reflected, and then it passes back through the film. Okay, so essentially the ray that enters into the material actually has to travel a distance of 2t, right? So it goes t down, and then when it gets reflected, it travels another t distance back up, right? Which means there's essentially a difference between the length or the distance that each of these rays travel, right? Ray 2 travels 2t further than ray 1, okay? Now, depending on the thickness of the material, when the two rays leave the material, right, when ray 1 and ray 2 are then traveling together and moving away from the film, those rays might either be in phase, in which case they interfere constructively, or they might be out of phase, in which case they interfere destructively. Okay, so let me show you just another image of what's going on here. Okay, so here's the same kind of example, right? We have a ray hitting the film, and then some of it passes into the film, and then kind of bounces in the film, and then leaves the film again. Okay, so depending on the thickness of the film, what we might notice is that these two waves might be in phase with each other, right? Meaning the crest from ray 1 matches up with the crest from ray 2, right? So we get an amplification, okay? So these two waves are in phase, and therefore they interfere constructively, okay? Now this occurs when the value, so if we look at this formula down here, we can kind of interpret what this formula is telling us, all right? So we will have constructive interference when the thickness of the film is some multiple of the wavelength of light, okay? And the way that you want to think about that, as the light ray is traveling in the film, so this portion here, right? If the ray that's traveling inside the film, if it travels an integer multiple of the wavelength, then when it emerges back out of the film, it'll be in phase with the original reflected wave, okay? And so essentially, this criteria enables us to develop, or enables the waves to interfere constructively, okay? Now, if that's not the case, right, if instead the waves do not interfere constructively, so as we can see here, the two waves, when they emerge, they're actually out of phase with each other, right? We can see the crest of ray 1 matches up with the trough of ray 2, so we have perfect destructive interference, okay? And as we can see, when the two rays leave the film, they're actually exactly half a wavelength apart from each other, right? If the crest of one wave matches up with the trough of the other, they're exactly half a wavelength separated from each other. They're half a wavelength out of phase, okay? And again, if we look at the formula, we kind of see that, right? We can see that the thickness of the film is some multiple, some half wavelength multiple, so we can see the m plus 1/2 of the wavelength, okay? Meaning that when the wave emerges, it'll be out of phase with the original wave, okay? And so we have two cases here where the outgoing waves will either be in phase or out of phase with each other. Okay. I know this is a lot to handle. I'll take a quick pause here and we can check in with each other. Yeah, so here we can see in the figure that we discussed here and in the formulas that we had here. Oh, Costa, you're gonna mute. Perfect. Okay. So we have, so in the figures that we discussed here, we have N1 is less than N2 is less than N3, meaning as we step through the materials, the indices of refraction get progressively larger, okay? But looking at this soap bubble right here, right, we can see in the soap bubble that we would go from air to whatever material the soap is back to air. And so we don't actually have this N1 less than N2 less than N3 scenario happening, okay? What we have instead is the material that's in the middle, so N2, is actually bigger than N1 and N3, all right? Now what's going to happen? Every single time a wave, so let's draw out another picture here just so we can kind of explain what's happening. So let's say we have a wave pulse, okay? And the wave is going from, oh, that didn't work so well. The wave pulse is traveling from so it's traveling from a less dense to a more dense material, okay? So you might have a wave, let's say, traveling from air to water as an example, okay? So this wave is incoming. Now, when it hits the boundary between the two material, what's going to happen is some of it's going to be reflected, right? And it turns out that the reflected wave gets inverted, okay? And then it travels back into the material, all right? So when the wave becomes inverted, it actually introduces a phase shift, okay? So whenever we go from less dense to more dense, we essentially go exactly half a wavelength out of phase from what we were originally traveling in, okay? And so we kind of, the formulas that we discussed up here in our first scenario where N1 was less than N2 was less than N3, we accounted for that flipping already, right? Because essentially we're going to have two flips. We're going to have a flip when we travel from the air to the soap, and then we're going to have another flip when we travel from the soap to the glass, let's say, okay? So essentially this is already accounted for in what we've already discussed, right? But when the light ray, so let's focus on this light ray right here. let's say N2 is bigger than N3. So we're going from a more dense medium to a less dense medium. So let's see what happens there. Is this familiar to anyone from last year? You should have discussed this last year a little bit. Maybe not. Okay, so when we instead, if we go from a more dense to a less dense material, then what's going to happen is when the wave gets reflected, it's actually going to be it's going to maintain its upright state. Okay, so it actually doesn't get inverted. All right, meaning it'll the reflected wave will be in the same phase as the incoming wave. Okay. Now, the whole result of this reflection or this inversion of the wave when it's reflected, it turns out that when we go from, or when the index of refraction of the thin film is bigger than the N1 or bigger than N3, we actually get a different set of formulas because we don't actually have that we don't have that flip. Okay, we don't have that flip on the second boundary. All right, and so what ends up happening if you look at the formulas here and you actually compare the formulas to what we had in the initial case, you can see that they're almost exactly opposite each other, right? And that's just due to the fact that we don't have that inversion when we go from a more dense to a less dense material. Okay, so I'll take a quick pause here. So yeah, I just summarize here. We have the following two sets of formulas, and we just have to kind of determine when we're going to use each one of them. Okay, so let's get into an example here. So consider a soap film that is the thinnest film that will produce a bright blue light. Okay, bright blue light when illuminated with white light. So the index of refraction of the soap film is 1.35, and the blue light is monochromatic, again meaning single wavelength, that has a wavelength of 411 nanometers. Okay, so let's just summarize that information. All right, so we have the wavelength that we're considering here is 411 nanometers, which is 411 times 10 to the negative 9 meters. All right, we're told the index of refraction of the soap film is 1.35. Okay. We also know that it seems like we have, like, the light is initially traveling through the air and then hits the soap film, and then we're gonna figure out what the bottom layer is going to be in a second. Okay, so n for air is just 1, or approximately 1.00. Okay. And so we're given two separate scenarios here. Okay, so we're going to calculate the thickness of the film if the soap covers a piece of glass with an index of refraction of 1.52. So glass with an index of refraction of 1.52. So let's draw out that scenario. Let's just draw out part A for now. So part A, what we have is we have air, we have the soap film, and then beneath the soap film we have glass. Okay, so air, we have an index of refraction of N1 is 1.00, soap N2 is 1.35, and then the glass N3 is 1.52. Okay. So that's the scenario we have. And what if we look at the question here, there's kind of a key word. Consider a soap film that is the thinnest film. Okay, so thinnest, that's important. We're going to deal with that in a second. That will produce a bright blue light. Okay, so essentially this interference is generating, or it's causing there to be a bright blue light at the end of it. Okay, so if it's a bright blue light, is that constructive interference or destructive interference? What do you guys think? Okay, so I'm definitely dealing with scenario one here, right? So I'm dealing with we want constructive interference, right? Because again, it's creating a blue light, a bright blue light afterwards. Okay. Also, we know that the index of refraction of the air is less than the index of refraction of the soap, which is less than that for glass, which means we are dealing with this formula right here. Okay, so I'll draw a little box around that. Boom. So we're going to apply this formula there. All right, so let's give it a try. So we have 2t equals n lambda over n film. Okay. Now there's one other piece of information which I mentioned, but we haven't discussed yet. So notice that it says the it's referring to the thinnest film. Okay. Now the thinnest possible film occurs when n in this equation, n is equal to 1 for the thinnest possible film. Okay, so essentially there could be multiple different thicknesses that would generate a blue light. Okay, but we're looking for the thinnest possible film. All right, so we set n is equal to 1 because if n was bigger than 1, if n was equal to 2 or 3 or 4, we could see that this equation would result in t being a bigger value as well, right? So if n is bigger, t gets bigger as well, but we're looking for the thinnest possible film, all right? So now we have everything we need, right? So 2t is equal to n, which we're setting to be 1. We know our wavelength is the wavelength of blue light, so 411 nanometers. And then our index of refraction for our film, so that's our soap, is 1.35. All right, so we can plug all these in and get a value for t. I get a value of 1.522 repeating times 10 to the negative 7 meters, or approximately 3 sig figs. Yeah, 3 sig figs. 1.52 times 10 to the negative 7 meters. Okay. Check my answer. I think I'm good though. Yep. Cool. All right. Okay, now let's change it up. Let's consider the second scenario here. Okay, so we're changing up the properties of the question here. So suppose the reflections occur instead. So instead, we change it up so that the soap film is on water. Okay, so instead of being placed on glass, we place the soap film on water, and water has an index of refraction of 1.33. Okay. And the question remains the same. Determine the thickness of the film that will produce the same blue color of reflected light. Okay, so for part B here, we're going to have a similar scenario. So I'm just going to copy this with one major difference. Okay, so instead of having glass as our substrate, we're going to have water instead. Okay, and the index of refraction of water is 1.33. Okay. Now, looking at this scenario instead, we should immediately notice that the index of refraction of our film, of our soap, is bigger than the other two, right? So here we immediately notice that N2 is bigger than both N1 and N3. Okay. And so what we want to do is we're actually going to use our second set of formulas for this part of the question, right? Because now we're not dealing with, they don't increase in order. Turns out that our film has the highest index of refraction of the other two, right? And so we're actually going to be using, again, we're still dealing with constructive interference. We're going to be dealing with this formula right here, okay? And so, yeah, we're still dealing with constructive interference, so we can just use that one. So 2t equals m plus a half lambda over n film. Okay, and in this case, for the thinnest possible film, we're going to be dealing with n is equal to 0 is the thinnest possible film. Okay, so let's plug in and see what we get. I get a value of 7.61 times 10 to the negative 8 meters. Okay. All right, I'll take a pause there. Okay, so last exercise here. So in solar cells, we have incoming light that passes through an anti-reflective coating to increase the efficiency of the cell. So this is the example I was mentioning earlier. So in this case, we have the following scenario. So we have waves coming from air. So N1 is equal to 1. And then this, the solar cell is treated with some coating, right? Some anti-reflective coating. So N2, we are told, is 1.45. Okay. And then this coating is on a substrate that has a index of refraction of 3.50. So substrate, there we go. N3 is equal to 3.50. Okay. And so immediately we notice that we're in the scenario of N1 is less than N2 is less than N3. So our indices of refraction progressively get larger as we go. Okay. So in this case, we need to maximize the amount of transmitted light. And so by doing that, we're trying to minimize the reflected light. So it says here, we're trying to minimize the reflected light. Okay, so essentially, we're not in a constructive interference scenario anymore. We want to have destructive interference occur, right? We don't want there to be any reflected light. Okay, so essentially, we're going to be dealing with either one of destructive or destructive formulas here. Okay. So determine the thickness of the anti-reflective coating that will minimize the reflection of light with a wavelength. So we're told the wavelength here is 7.00 times 10 to the negative 7 meters. And we are looking for the thickness of the coating that will make that happen. Okay. So we notice immediately that N1 is less than N2 is less than N3, and that means we're dealing with this set of formulas here, right? And because we're looking for destructive interference, we want there to be no reflected light or as little reflected light as possible. We're going to be dealing with this formula right here, right? So destructive interference, where N1 is less than N2 is less than N3. So let's give this a go. So we have 2t equals m plus a half lambda over n film. Okay. Now notice this question doesn't make any reference to, like it doesn't say the minimum thickness of the coating. Like the last question said, what was the thinnest film possible to make the scenario happen, right? This question doesn't have any of that, but I'm assuming we can still take the minimum thickness, right? Some questions, I think, yeah, so like looking through the types of questions in the textbook, it says calculate the smallest thickness, calculate the thickness of the oil slick so that you cannot see yellowish light. So usually it's dealing with the minimum thickness, okay, in most of the questions in the textbook. I think it'll specify otherwise, all right? So here again, we're assuming the minimum thickness, which means m is going to be 0 in this formula here. And then we can do the same thing, just plug in and solve, right? So 2t is equal to 1/2 lambda, so our wavelength, over n film, which is 1.45. Okay, and I can calculate my t value. So let's see what we get. I get a thickness value of 1. How many sig figs? 3 sig figs. So 1.21 times 10 to the negative 7 meters. All right, and that's that. That is all I've got. That's it. That's all. So I'll pause here, and if you guys have questions, let me know.